Hello, Pre-Algebra students. This is Chapter 8.9, Graphs of Linear Inequalities. In previous sections, we've solved inequalities in one variable, and now we're going to graph inequalities in two variables. Let's get started. Let's start with a linear equation in two variables. 2x minus 3y equals 6. In order to turn this into a linear inequality, all we need to do is replace the equal sign with a greater than or equal to, a less than or equal to symbol. For example, 2x minus 3y would become 2x minus 3y is less than 6. This is our linear inequality. An ordered pair xy is the solution of a linear equality if substituting the values of x and y into the inequality produces a true statement. Let's check solutions of this linear equality. 2x minus 3y is less than 6. The first ordered pair I'd like to test is 0, 1. We'll begin by substituting. 2 times 0 minus 3 times 1 is less than 6. 2 minus 3 is less than 6. Negative 1 is less than 6. So this statement is true. 0, 1 is a solution for 2x minus 3y is less than 6. Let's test another. The next ordered pair I'd like to test is 4, negative 2. We begin by substituting. And now we solve. 8 plus 6, or 14. This is not true. 14 is not less than 6. So 4, negative 2 is not a solution for the inequality 2x minus 3y is less than 6. The graph of a linear inequality in two variables is the set of points in a coordinate plane that represent all the inequality's solutions. All the solutions of 2x minus 3y is less than 6 lie on one side of the boundary line. This is our boundary line here. Okay? The boundary line divides the plane into two half planes. The shaded half plane is the graph of 2x minus 3y equals 6. So everything in this area is a solution. Everything in this area is not. So how do we find that boundary line? Quite simply, you find the equation of the boundary line by replacing the inequality symbol with an equal sign. Graph that equation. So this line here represents the equation 2x minus 3y equals 6. We use a dashed line to indicate less than or greater than, and then we use a solid line if it's less than or equal to or greater than or equal to. Make sense? Then we're going to test a point in one of the half planes to determine whether it's a solution to the inequality. So we would go back to the ordered pairs that we tested before. So our first ordered pair was 0, 1. So here would be that point. Okay, that is a solution to the inequality. So we would shade that half of the graph. Okay, let's test our other point, which was 4, negative 2. Okay. That does not fall in the shaded portion and is thus not a solution to the linear inequality. Let's work through the process of graphing a linear inequality. We're going to graph y is greater than or equal to 2x plus 4. Our first step is to draw the boundary line, which we find by graphing the equation y equals 2x plus 4. So our y-intercept is 4. Our rise over run is 2 over 1. So we're going to go up 2 over 1, down 2 over 1, down 2 over 1. And here is our line, okay? So let's go ahead and draw that line in. Sorry, it's a little crooked. You know all about my art skills by this point. Okay, now let's test a point. Start with 0, 0, just because, okay? 0, 0 falls here. To determine if this side should be our shaded side, we'll now substitute 0, 0 into our inequality. Y is greater than or equal to 2 times 0 plus 4. Oops, I guess our y should have been 0 there too, huh? Sorry about that. Is 0 greater than or equal to 4? No. We now know that 0, 0 is not a solution, so we aren't going to shade that half plane. We're going to shade the other half plane to represent our set of solutions. Remember, this set of solutions does not just include the ordered pairs with integer coordinates. It includes any point in that shaded area, okay? Now let's graph inequalities with a single variable. We're going to graph x is less than 3 and y is greater than negative 2. Let's begin with x is less than 3. We'll begin by graphing x is equal to 3 using a dashed line. Remember, we use a dashed line because it's just greater than or less than and doesn't include equals. So 3 itself is not a point included on the line. Sorry, it's hard to make dashed lines with my stylus. Apologies. So there's my sort of dashed line on 3, x equals 3. Now let's test the point 0, 0. X is greater than 3. If the value, or less than 3, excuse me, if x is valued at 0, this is a true statement. Therefore, we're going to shade in the half plane that contains 0, 0. And that is our graph of x is less than 3. Now let's graph y is greater than negative 2. We begin by graphing y is equal to negative 2 using a solid line, because negative 2 is included in our set of solutions. So here is our graph of y equals negative 2. Now let's test a point. 0, 0. 0 is greater than or equal to negative 2. That is a true statement. Therefore, we will shade in the half plane that contains 0, 0 to represent y is greater than or equal to negative 2. Now try this out on your own. Graph the inequality given in a coordinate plane. Make sure that your equation is in slope-intercept form before you begin. Press pause while you work. We have one last idea to explore before we finish up Chapter 8.9. We're going to finish up this section by applying what we've learned about writing and graphing a linear inequality to solve a real-world problem. Let's say we have 100 pounds of clay to use for making bowls and vases. We need 5 pounds of clay for each bowl, and we need 2 pounds for each vase. So first, let's write an inequality describing the possible number of bowls and vases that we could make. Then we'll graph that inequality, and then we'll give 3 possible combinations of bowls and vases that we could make with our 100 pounds of clay. Okay, so let's begin by letting x be the number of bowls that we can make, and y being the number of vases that we can make. So let's write a verbal model to help us understand. Let's begin with clay needed per bowl. And we're going to need to multiply that by the number of bowls. Then we need to add that to the clay we need per vase, right? Multiplied by the number of vases. And this number will need to be less than or equal to our total amount of clay, or 100 pounds. Okay, we want to get as close to that 100 pounds as possible. So the amount of clay we need is 5 pounds, right? And x is our number of bowls. The amount of clay we need per vase is 2 pounds, and y represents our number of vases. That's going to be less than or equal to 100 pounds. All right, we've got our equation. Let's graph this. Let's take a look at the graph of this linear inequality. Please excuse the slightly curved picture. We start by graphing our boundary line, which is 5x plus 2y equals 100. A solid line is used here because it is less than or equal to. And here is our boundary line. Okay. The next thing we'll do is we'll test point 0, 0 in the inequality. So 5 times 0 plus 2 times 0 is less than or equal to 100. That would give us 5 plus 2 is less than or equal to 100, and 7 is indeed less than 100. So we shade this half that contains 0, 0, because that contains all of our possible solutions. Notice that we don't go into negative numbers. We can't have a -1 bowl or a -2 vase. Just doesn't work. So we keep our domain in positive numbers. Now we're going to choose any 3 points on the graph with whole number coordinates. A couple of examples here would be 5, 20, right? So we could make 5 bowls and 20 vases. Or we could make 10 bowls and 10 vases. Or you could make, if you wanted, just 20 bowls and not make any vases at all. And that would use all of your clay. Okay? So that's the final piece of solving that particular inequality. We gave 3 possible combinations of bowls and vases that we could make. You could continue to choose combinations as long as they're in the blue shaded portion of this graph. This wraps up chapter 8.9 for us. When I see you tomorrow, we'll do lots more work with writing and graphing linear inequalities with 2 variables. See you then.